Welcome to the final lesson of the periodic table. So at the end of this unit, we're going to be talking about periodic table trends. And these are patterns that are present in the periodic table. And it kind of will help explain a little bit more of why it's set up the way it is and how within its setup we can predict certain characteristics of certain elements. In order for us to really understand how these trends work, we're going to start by just explaining the basic principles of Coulombic attractions. So when we're talking about an attraction of a positive and a negative, we really have to focus on two key factors. Now, as it pertains to the atom, one of the two factors is the number of protons. This is vital. Right? The more protons that are in the nucleus, the greater the force of attraction an electron will have towards the nucleus. So in the two images that have been presented, we can see a magnet of one proton maybe only has a reach of a short distance, especially as we compare the reach of 10 protons. So the more protons you add, the stronger the magnet of the nucleus pretty much becomes. That's the first thing that we need to have in our minds. The second thing that we need to have in our minds is the distance of the positive and negatives. So it's very much like a magnet. A magnet is very attracted to a refrigerator or magnetic surface when they're close to each other. But if they are farther away, that attraction is much weaker. Same thing goes for protons and electrons. Electrons that are really close to the nucleus feel a stronger attraction than the electrons that are further away from the nucleus. So distance and amount of protons are the two things that are most important for where we are about to go. One last thing we'll talk about is the shielding effect. And I can pretty much sum this up rather quickly. The shielding effect basically says an electron that is very close to the nucleus with no other layers blocking it will feel no shielding effect. They get no effect on anything blocking them. So that attraction is very strong. But an electron that is in the third energy level will have to feel the effect of this level blocking it and this level blocking it. So there is shielding here. Is shielding, right? So shielding is just if there are electrons in the way, it's going to block it. And the more shielding that there happens to be, the weaker the attraction towards the nucleus you will get. So the attraction on our left is a strong attraction versus over here on the right side, this will be a much weaker attraction due to shielding. So the three trends that we are going to discuss, and we're going to have to keep into account shielding and attraction of protons and electrons, are as starting with atomic radius. Atomic radius is the distance from the nucleus to the valence electrons. It's the size of the atom, right? That's exactly what it is. So there are two different things that you need to be responsible to know, and that is what is the trend and why is the trend the trend. So I'll show you how we know what the trend is, and then I'll explain why the why is what it is. In order for us to do this, we need to look in our reference table. Now, we're looking to find the radius of lithium and the radius of fluorine. And so if we go to our reference table and we find lithium right here, and we find fluorine right here, what we can see in this right side of the table is the actual values of atomic radius. So lithium is 130, fluorine is 60. So the reference table actually gives us the trend. As we go from the left side of the table where lithium is to the right side of the table where fluorine is, all radii decrease. They decrease from the left side to the right side. The reason is a little bit more complicated. And the reason is because the number of shells stays the same. There are 2 shells in lithium. There are 2 shells in fluorine. There are more protons in fluorine than there are in lithium. So this goes back to the magnet that we were talking about. The magnet of fluorine is much stronger than the magnet of lithium. And as a result, it pulls the electrons in tighter, causing the size of the atom to decrease. It has nothing to do with how many electrons there are. It has everything to do with the fact that the positive charge of the nucleus in fluorine is a much stronger positive charge than the positive charge in lithium. Now, if we go down a group, we see a different trend. Down a group, we see an increase in radius. We see the radius go from 130, let's check our reference table for sodium, to 160. And now we're seeing an increase in atomic radius, an increase in the size of the atom from top to bottom. And this reason is because there are more shells. There's a whole third shell, right? 1, 2, 1, 2, 3. So naturally, if you put another layer on an onion or another Russian nesting doll on the outside of a smaller Russian, it gets bigger, and the atom does the exact same thing. Okay, the next term and trend that we have to understand is a term called ionization energy. Now, ionization energy is a definition that means the energy required to remove the most loosely held valence electron. Simply put, we want to how well does something lose an electron? So the trend, I'll keep saying, the trend is given to us by the table. Lithium has a first ionization energy of 520. Fluorine has an ionization energy of 1,681. So 520, 1,681. So it should be really easy for you to see that as you go across the periodic table, the value of ionization energy increases. And that is the what. That is the what of the trend. What is the trend? Increase from left to right. The why is the same reason as the radius shrinking. The radius shrunk because there were more protons pulling in the electrons. Here, there are more protons pulling in the electrons, making it harder to remove an electron than the easier lithium. So it's the same reason, but we're talking about a different characteristic of the same 2 atoms. Down a group, We have 520 ionization energy here. Go back to our reference table. Sodium, ionization energy, 496. Okay? We are dealing with a decrease as we go from the top to the bottom of a group. That is the what. The why is that there are more shells. And therefore, the valence electrons are further away from the nucleus. So, the farther away the electron is from the nucleus, third shell versus second shell, the easier it is to remove the positive and negatives attraction. It's also the reason why the atom is bigger as you go down a group. There are more shells in play. Because you got to think, especially with this atom is responsible for holding those 2 in the first shell, these 8 in the second shell, and this 1 electron all the way out in the third shell, it kind of gets lost. It's easy to lose because it's so far away and the nucleus is worried about so many other electrons. Versus here, there's not as many electrons that the nucleus is worried about. Sure, it's worried about the same 2 in the first shell, right? But this third one, it would be the first one to go, but it's much closer, therefore much harder for it to be removed. So now we'll go on to the final term, electronegativity, which is basically the opposite of ionization energy. In this case, we're talking about how well does an atom gain electrons. This is not going to be a large number. These numbers are scaled from 0 to 4.0. And they measure how great an atom is at bringing in new electrons or how bad an atom is at gaining new electrons. 0 being bad, 4.0 being great. So, again, our reference table will give us the trend. The what of the trend is always at our disposal. Lithium, electronegativity, 1.0. Fluorine, electronegativity, 4.0. Lithium, 1.0. Fluorine, 4.0. The trend, as you go across the periodic table, is an increase in electronegativity. This is the what, and it is not something needed to be memorized. The why needs to be reasoned. So ask yourself, why do you think fluorine is better at gaining electrons versus lithium, which is bad at gaining? Structurally, the only difference between lithium and fluorine is their nucleus. Fluorine has 9 protons. It is a stronger magnet. Lithium has 3 protons. It is a weak magnet. Both of these have 2 electron shells. Relatively speaking, fluorine is a much stronger nucleus than lithium. So the reason is that there are more protons. And when there are more protons, the radius shrinks, pulling electrons in tighter. This would make adding 1 more electron very easy for fluorine. finally, we could talk down a group. So down a group, we're dealing with lithium having a 1.0, and we're dealing with sodium having an electronegativity of 0.9. The trend is simple. As you go down the group, the electronegativity decreases. The reason is the same reason as the other two trends when you go down a group. There are more shells. And when valence electrons are farther from the nucleus, we know that they are easy to remove. And if the farthest valence shell is easy to remove, well, then it's going to be hard to gain. And as atoms get bigger and bigger and bigger, it becomes harder and harder for them to add new electrons. I hope that helps you understand periodic table trends as it pertains to the New York State Chemistry Regents. And I hope you've enjoyed this video. Make sure you hit a like.